Alright guys, so we're going to move on to 5.2 now. 5.2 deals with rational functions. And last time we were talking about polynomial functions, and we kind of weren't allowed to have any fractions, like they couldn't have like a thing on top, like a numerator and a denominator with stuff on top and the bottom. And with the rational function, now we have that, okay? So let's look at the most very basic rational function. It would be one we've seen before already, that one. The reciprocal function, 1 over x. That would be a rational function. It is a fraction, okay? This is not a polynomial function. We would not say it's a polynomial function because it has an x in the denominator. That x would have like a negative exponent. So we're not allowed to say this is a polynomial function, but it is a rational function. So now let's look and see what's going on with rational functions. Let's say we have this. Here's our, let's look at the graph of this real fast. Remember how the graph of this looked? It looks something like this. That, like that, and like that. That was the graph of the reciprocal function. It like if we go in this direction, it got really close to the x-axis, but never really ever touched it, because that would be when this equals 0. And really, this can't equal 0. This is not allowed to equal 0, because the only time this would equal 0, like what value for x could you put in that would make this equal to 0? Think for a second. Can't do it. All right? There's no value for x that you could put in right here that would make this equal to 0, because a fraction is only equal to 0 when the numerator is equal to 0, and this numerator is always 1. So there's no way you can make this equal to 0. So it's never going to touch the x-axis. Now the other thing is, I'm never, like, if you look at the domain of this, I can't plug in 0 for x. 0 is not allowed to go into this function. I can't put 0 into this machine. 0 breaks the machine. Because if I put in 0, I would do 1 over 0 and it's undefined. So I can't have any values at x equals 0, which x equals 0 would be the y-axis, would be this vertical line at the y-axis. So what I end up with these kind of imaginary lines that aren't on the graph, but kind of determine where the graph goes. There's like one that goes this way, bump, 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 like I'm just put like a little dashed line, bump, 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 here, okay? And this was at y equals 0, the horizontal line, y equals 0. The graph gets really close to this line, doesn't really ever touch it, because this can never equal 0. The other line we have is this one, this vertical line right here, and that's the line x equals 0. Vertical lines are x equals. And the graph can never touch that one because that's not in the domain. I am not allowed to plug in 0 for x, because then it gets undefined. So we end up with these dashed lines where the graph is like not allowed to touch. These lines are called asymptotes. Asymptotes. All right? I say asymptote, but you know, that's wrong, and that's okay. So asymptotes, all right? So the graph has asymptotes, has a horizontal asymptote at y equals 0 and a vertical asymptote at x equals 0. Lines that the graph gets really close to, but never really touches, right? It's not allowed to touch, okay? So real quick, let's look and see where vertical asymptotes come from. Vertical asymptotes, okay, so vertical asymptotes happen at numbers that are not in the domain. All right, whenever numbers are not in the domain, then that doesn't work. So this particular one, the reciprocal function, will have, so this happens at numbers not in domain. I should say x values not in domain, but I'm not a math book. At numbers not in the domain. So then that would be like, for example, for this one, it would be at x equals 0. If x is 0, 0 is not in the domain of this function, so we're going to have a vertical asymptote there. Right? If I just make up another one here, let's say we had like f of x equals 3x over x plus 4. Right? Where would there be a vertical asymptote here? Well, it would be at whenever the denominator is equal to 0. So you say x plus 4 equals 0, so x equals negative 4. That's where our vertical asymptote is going to be. And if we look at the graph of this, actually you can see it pretty good. If we just quickly sketch the graph of this little thing, it would look like this. Here's this. It would be 1, 2, 3, 4. So here's x equals negative 4. That's the vertical asymptote of x equals negative 4, and the graph would look something like this. And then come in this way. Like that. That's what the graph would kind of look like. And so it would have a vertical asymptote at x equals 4. Okay? So something similar, something sort of like this, at least as far as the vertical asymptote piece is concerned. Okay, this might be a little bit scooted up or down, but I mean that's where the vertical asymptote is going to go. Okay, so something like that. So that's where vertical asymptotes come from. Next, we're going to take a look at horizontal and other kind of asymptotes before we start getting before we finish off with these things. All right, here we go.